somewhere in the scorched interior of Australia, where the earth itself splits open under a sun that never seems to relent. There is a snake so quietly lethal that a single bite carries enough venom to end the lives of more than 100 adult human beings. Not 10, not 50, over 100. And yet, in the entire recorded history of human civilization, this animal has never killed a single person. Not one. Let that settle in your mind for a moment, because it is one of the strangest contradictions in the entire animal kingdom, the most toxic land snake ever measured by science. The creature whose venom is so devastatingly potent that it makes a king cobra look almost gentle by comparison, has a body count of exactly 0. This is the Inland Taipan. Some people call it the fierce snake, which is one of the greatest misnomers in all of biology, because the word fierce does not describe the snake's temperament. It describes what its venom can do. In personality, the Inland Taipan is about as aggressive as a house cat that just wants to be left alone. It would rather slide into a crack in the dry earth and vanish from your sight than confront you. It is shy. It is reclusive. It lives in one of the most desolate, sun-blasted, sparsely populated regions on the planet. A place where the average person will never set foot in their entire lifetime. And that, in many ways, is what makes this snake so fascinating, because while the rest of the world's dangerous animals earn their fearsome reputations through frequent encounters with people, through aggression, through proximity to villages and farms and cities, the Inland Taipan has earned its reputation entirely through chemistry, pure, cold molecular lethality measured in a laboratory, far from the cracking clay floodplains where this ghost of the outback actually lives. Now, here is the fact that is going to stay with you. When researchers at the Commonwealth Serum Laboratories in Melbourne tested the venom of the Inland Taipan against laboratory mice in the 1970s, they measured something extraordinary, the subcutaneous LD50, which is the standard measurement for how much venom it takes to kill 50% of a test population, came back at 0.025 milligrams per kilogram of body weight. To put that in perspective, the eastern diamondback rattlesnake, one of the most feared snakes in North America, registered at 11.4 milligrams per kilogram. That means the Inland Taipan's venom is roughly 450 times more potent, drop for drop, than a rattlesnake's. Even the Indian cobra, a snake that kills thousands of people every year across South Asia, registered at 0.565 milligrams per kilogram, making the Inland Taipan's venom more than 20 times stronger. And when researchers calculated just how much killing power a single average bite contains, the numbers were staggering. One bite from an Inland Taipan delivers an average of 44 milligrams of venom, with a maximum recorded dose of 110 milligrams. That average bite, all by itself, carries enough toxin to kill approximately 250,000 mice. 250,000 mice from one bite. So tonight, as you settle in, we are going to spend some real time with this extraordinary animal. We are going to walk through its strange and interrupted scientific history, a story involving misidentification, 90 years of mystery, and a dramatic rediscovery in the remote Queensland outback. We are going to trace its evolutionary ancestry back through millions of years to the ancient marine serpents that first swam to Australian shores from Asia. We are going to immerse ourselves in its habitat, the vast, cracking clay floodplains of the Channel Country, where summer temperatures can climb past 50 degrees Celsius, and the landscape looks like something from another planet. We are going to dissect, in detail, the chemical machinery inside its venom glands, the neurotoxins, hemotoxins, and procoagulants that make this snake's bite arguably the most sophisticated chemical weapon in the entire reptile kingdom. We will explore its hunting strategies, its intimate relationship with the boom and bust cycles of the long-haired rat, and the seasonal transformation that sees this snake literally change color between winter and summer. And we are going to talk honestly about what happens when a human being is bitten, the handful of recorded cases, the anti-venom that has saved every life, and the promising medical research that may one day turn this deadly venom into life-saving medicine. So get comfortable, close your eyes if you like, and let us travel together to the heart of the Australian outback, to the land of cracking earth and vanishing rivers, where the most venomous snake on the planet lives its quiet, secretive, utterly remarkable life. The story of how science came to know the Inland Taipan is, in itself, one of the strangest tales in the history of herpetology. Because this snake was not simply discovered and then studied, it was discovered, promptly lost for nearly a century, and then rediscovered under dramatic circumstances in the remote Queensland outback. For 90 years, the Inland Taipan existed as little more than a footnote in dusty museum records, a phantom species that some researchers suspected might not even be real anymore. The year was 1879. Two snake specimens arrived at the National Museum of Victoria in Melbourne, collected from the junction of the Murray and Darling Rivers in northwestern Victoria. The naturalist Frederick McCoy examined them and published a formal description, naming the species Deminia microlepidota, which translates roughly to small-scaled. He classified it as a type of brown snake based on its general appearance and the scaling patterns he observed. 3 years later, in 1882, a third specimen turned up near Burke in New South Wales. The naturalist William John Macleay examined this one independently, and believing it to be a different species entirely, named it Deminia ferox, which means fierce. He had no way of knowing he was looking at the same animal McCoy had already described, and that was it. After those 3 specimens, collected from 2 locations in the 1870s and 80s, the snake simply vanished from the scientific record. No more specimens were collected. No researchers encountered it in the field. For nearly a century, the small-scaled snake existed only as a handful of preserved specimens in museum jars, gathering dust while the world moved on. During those lost decades, the taxonomic history of the snake became hopelessly tangled. In 1896, George Albert Bullinger reclassified both McCoy's and Macleay's specimens into the genus Eudechs, the black snakes, calling them pseudeches microlepidatus. In 1956, James Roy Kinghorn, working only from published descriptions and notes, because he had no fresh specimens to examine, recognized that McCoy's and McLee's snakes were the same species and proposed the new genus Paradomancia. Then in 1963, Eric Worrell muddied the waters further by suggesting that Paradomancia microlepidatus was actually the same species as the coastal taipan, Oxyuranus scutulatus, a snake that was already well known and widely feared across northern Australia. Without living specimens to compare, it was nearly impossible to sort out the confusion. The breakthrough came in September of 1972, and it came from an unlikely source. A grazier from one of the remote Channel country stations west of Windora, in far southwestern Queensland, sent a snake head to the Queensland Museum. He did not know what kind of snake it was. He just knew it was unusual. The head landed on the desk of Jeanette Kavesvich, a herpetologist working at the museum, and her colleague, Charles Tanner. They recognized immediately that this was something extraordinary. Kavesvich and Tanner traveled to the remote station, and after searching the sun-blasted landscape of cracking clay and sparse vegetation, found 13 living specimens. 90 years after Frederick McCoy's original description, the ghost snake had been found again. The small-scaled brown snake that had puzzled naturalists in the Victorian era was alive and well, hiding in the deep soil cracks and abandoned rat burrows of one of the most remote landscapes on Earth. What followed was a period of intense scientific work. In 1976, Kavesvich and Wami argued that the species deserved its own genus, Paradomancia, separate from both the brown snakes and the black snakes. But by 1981, Kavesvich, along with McDowell, Tanner, and Mengden, made a convincing case based on comparative anatomy, chromosome analysis, and behavioral studies that this snake actually belonged in the same genus as the coastal taipan, Oxyuranus. The name Oxyuranus had been coined back in 1923, derived from the Greek words oxys, meaning sharp or needle-like, and auranos, meaning an arch or the vault of the heavens. It referred to the distinctive needle-like process on the arch of the snake's palate, a feature that separated taipans from all other elapid snakes. With the reclassification official, the coastal taipan, which had previously been known simply as the taipan, became the coastal taipan, and the rediscovered phantom became the inland taipan, Oxyuranus microlepidatus. The Aboriginal people of the region, of course, had known about this snake all along. To the communities living around what is now called Goyder Lagoon in northeast South Australia, the snake was called Dandrabilla. The name taipan itself was coined by the anthropologist Donald Thompson, borrowed from the Wik-Munkin Aboriginal people of Central Cape York Peninsula in Queensland, who used the word in reference to an ancestral creator being connected to the rainbow serpent of Aboriginal mythology. So while Western science spent 90 years in confusion, the original inhabitants of the land had been living alongside this animal, naming it, understanding its habits, and respecting its power for thousands of years. Today, we also know that there are 3 recognized species in the genus Oxyuranus. Beyond the inland and coastal taipans, a 3rd species was described in 2007 after a single specimen was caught in the desert east of the Walter James Range in Western Australia in 2006, initially mistaken for a small western brown snake. Molecular analysis confirmed it as a new taipan species, formally named Oxyuranus temporalis. The Western Desert Taipan, or Central Ranges Taipan, a 2016 genetic analysis confirmed the relationships within the genus, showing that the speckled brown snake, Pseudonaga guttata, was an early offshoot of the lineage that gave rise to taipans, and that the Central Ranges taipan branched off from the common ancestor of the inland and coastal taipans, which then diverged from each other into the 2 distinct species we know today. To understand how the inland taipan came to be the lethal precision instrument it is today, you have to go back a very long way. Not just thousands of years, or even millions. You need to go back to a time before Australia had venomous snakes at all. The inland taipan belongs to the family Elapidae, a vast and ancient group that includes cobras, mambas, coral snakes, sea snakes, and the entire dazzling radiation of venomous land snakes that dominates the Australian continent. Elapids are front-fanged snakes, meaning they possess short, hollow, fixed fangs at the very front of their upper jaw, connected by a duct to venom glands that sit behind the eyes. This delivery system has been compared to a hypodermic syringe, a high-pressure injection apparatus that allows the snake to deliver a precise dose of venom deep into the tissues of its prey. With each strike, the family Elapidae is believed to have originated in Asia. Phylogenetic studies, which reconstruct evolutionary trees using DNA sequences, consistently show that the most basal, or oldest branching, lineages within the Elapid family are predominantly Asian. From this ancestral Asian homeland, Elapids spread outward, reaching Africa and the Americas roughly 40 million years ago. But their arrival in Australia came later, approximately 25 million years ago, during the late Oligocene or early Miocene epoch, and how they arrived is itself a remarkable story. For decades, scientists debated whether the ancestors of Australian elapids had arrived over a land bridge or had somehow crossed water. Research from the University of Adelaide, published in the journal Genes, provided compelling evidence for the aquatic route by comparing the genomes of Australian land elapids, like tiger snakes and brown snakes, with those of marine and semi-marine sea snakes and their Asian relatives. Researchers discovered that the ancestor of all Australian elapids had accumulated certain self-replicating genetic elements, known as jumping genes or transposable elements, that were not present in their land-dwelling Asian relatives. These genetic elements appeared to have been acquired from marine organisms, strongly suggesting that the earliest Australian elapids had gone through a period of marine adaptation. They had, in essence, swum to Australia. When these ancestral elapids arrived on Australian shores, they found a continent that was largely devoid of advanced venomous snakes. Vipers, which dominate the snake fauna of Africa, Asia, Europe, and the Americas were entirely absent from Australia. The existing snake fauna consisted mostly of pythons and other non-front-fanged species. This ecological vacuum created an extraordinary opportunity. The elapids underwent what biologists call an adaptive radiation, a rapid burst of diversification in which a single ancestral lineage evolves into a wide array of species, filling many different ecological roles. In the case of Australia's elapids, this radiation produced over 100 terrestrial species, from tiny burrowing snakes barely longer than a pencil to the massive taipans and king brown snakes, occupying virtually every available terrestrial snake niche on the continent. The genus Oxyuranus, the taipans, sits within a broader evolutionary grouping that also includes the brown snakes of the genus Pseudonaja. These two genera are sister groups, meaning they share a more recent common ancestor with each other than either does with any other genus. Molecular clock estimates suggest that the Oxyuranus and Pseudonaja lineages diverged from their common ancestor roughly 10 million years ago during the late Miocene epoch. Within the taipan genus itself, the inland and coastal taipans diverged from each other millions of years after that, with estimates suggesting a split around 5 to 8 million years ago. Though precise timing remains debated, the Central Ranges taipan, described in 2007, is the sister lineage to both, having branched off from their common ancestor earlier. What is particularly striking about the taipan lineage is its extreme dietary specialization. Unlike the brown snakes, which are generalist predators feeding on a mix of mammals, lizards, and frogs, all three taipan species feed exclusively, or almost exclusively, on mammals. This is a unique trait among Australian eelpids. Every other genus on the continent includes species with broader diets, but the taipans are committed to warm-blooded prey fully, and this dietary commitment, this evolutionary decision to hunt only mammals, is almost certainly what drove the inland taipan's venom to such extraordinary levels of potency. When your entire survival depends on killing fast-moving, bite-capable rodents that can inflict serious wounds with their teeth, you need a venom that works quickly, decisively, and overwhelmingly. The inland taipan's venom is not an accident of nature. It is the product of millions of years of evolutionary pressure, refined by the demands of hunting dangerous prey in a harsh and unforgiving landscape. The fossil record for elapid snakes in Australia, while sparse, supports this picture. Vertebral and cranial remains of elapid snakes have been collected from fossil assemblages at Riverslea in northwest Queensland. Most date to the Miocene epoch, but one specimen may be as old as the late Oligocene, roughly 23 to 24 million years ago. This is tentatively assigned to the genus Laticata, the sea krites, and if the assignment is correct, it implies that the basal divergences among Australasian elapid lineages had already occurred by the early Miocene, much earlier than many previous estimates suggested. This timeline aligns with a scenario in which elapids arrived in Australia through a marine phase, quickly colonized the land, and then underwent a spectacular adaptive radiation that produced, among many other species, the Taipans. If you were to visit the homeland of the Inland Taipan, you would find yourself standing in one of the most austere and inhospitable landscapes on the planet. The interior of eastern Australia, where the borders of Queensland, South Australia, and the Northern Territory converge, is a place of extremes. Summer temperatures regularly exceed 40 degrees Celsius, sometimes climbing past 50. Rainfall is sparse and unpredictable, often arriving in sudden, dramatic downpours that can turn the bone-dry floodplains into temporary shallow seas before the water evaporates or seeps into the ground, and the land returns to its cracked, desiccated state. The vegetation is minimal. Scattered chenopod shrubs, stands of lignum, and the occasional eucalypt clinging to life near a watercourse. This is not a lush jungle or a teeming savanna. This is the outback at its most stripped down and elemental, a place where survival requires absolute adaptation to scarcity. The Inland Taipan's core range centers on the Channel Country of southwestern Queensland. The vast network of braided river channels and floodplains associated with the Cooper Creek and Diamantina River systems. The snake has been observed in locations like Diamantina National Park, Durry Station, Morney Plains Station, and Estrella Downs National Park within Queensland, and in the Marion-Naminka Natural Resources Management District in South Australia, including areas around Goyder Lagoon, the Tarari Desert, Sturt Stony Desert, Coonji Lakes, and the Naminka Regional Reserve. An isolated population also exists near Coober Pedy in South Australia. Historical records from the 1870s and 80s placed the species at the junction of the Murray and Darling Rivers in northwestern Victoria and near Burke in New South Wales. But the snake has not been observed in either state since then and is presumed to have been extirpated from those areas. The key to understanding the Inland Taipan's habitat preferences lies in the soil. This snake is intimately associated with the deep cracking clays and cracking loams of the outback floodplains. These are black soil plains, ancient landscapes where the clay-rich earth expands when wet and contracts when dry, forming deep, dramatic fissures and crevices that can extend a meter or more into the ground. For the Inland Taipan, these cracks are everything. They provide shelter from the punishing sun, protection from predators, a stable microclimate during temperature extremes, and access to the underground burrow systems of rodents. The snake also uses abandoned animal burrows, rock crevices, and sinkholes as refuge sites. In some cases, the taipan will occupy the very same burrow system as its prey, hunting the rats and mice that shelter in the same network of underground passages. The Inland Taipan will also venture onto nearby gibber plains, those vast stretches of desert pavement covered in smooth, wind-polished stones, as well as sand dunes and rocky outcrops, provided there is adequate cover available. But the cracking clay floodplains are the heart of its world. This is where prey is most abundant, where shelter is most available, and where the snake's entire lifestyle, from hunting to breeding to thermoregulation, plays out across the seasons. Few people live in this country. The Channel Country Stations, vast cattle ranches that cover hundreds of thousands of acres, may have only a handful of residents. Towns are few and far between, and many of the roads are unsealed tracks that become impassable after rain. This extreme remoteness is one of the primary reasons the Inland Taipan so rarely encounters human beings. You could live your entire life in Australia, even in Queensland, and never come close to the Inland Taipan's range. The snake and its habitat exist in a kind of splendid isolation, cut off from the populated coastal regions by hundreds of kilometers of arid land. The climate of this region imposes strict rules on the Inland Taipan's daily and seasonal behavior. The snake is primarily diurnal, meaning it is active during the day, but its daily window of surface activity is narrow. During the warm months, it emerges in the early morning, spending a brief period basking near the entrance of a soil crack or burrow to raise its body temperature, then foraging along the cracking clay landscape for prey. By mid-morning, as the sun climbs higher and the ground temperature becomes dangerously hot, the snake retreats underground and remains hidden for the rest of the day. During cooler months, it may extend its activity into the afternoon, and during the most extreme summer heat, there is some evidence that the snake can shift its activity to a more crepuscular or even nocturnal pattern. Though it is primarily a daytime predator, this habitat shapes every aspect of the Inland Taipan's existence. The cracking clays provide the stage for its hunting dramas. The deep fissures supply its shelter. The sparse vegetation keeps the landscape open enough for a fast-moving snake to navigate efficiently. And the boom and bust rainfall patterns drive the population cycles of its prey. Remove any one of these elements, change the soil type, fill in the cracks, alter the rainfall patterns, and you would fundamentally disrupt the life of the Inland Taipan. This is a specialist animal in a specialist landscape, and its survival is woven into the geology, the climate, and the ecology of the Australian interior in ways that are both elegant and precarious. The Inland Taipan is a medium to large snake, with adults averaging around 1.8 meters in total length, though large individuals can reach 2.5 meters. The largest reliably measured specimen on record was a female with a snout-to-vent length of 170 centimeters, and the longest total length reported is 250 centimeters, or just over 8 feet. There is no significant difference in average length between males and females, though males tend to have slightly longer tails relative to their body size, a feature common in snakes that carry paired hemipenes in the base of their tails. The body is slender but robust, built for speed and agility rather than brute constriction. The head is deep, rectangular, and noticeably distinct from the neck, giving the snake a purposeful, wedge-shaped profile. The eyes are of moderate size, with blackish-brown irises and round pupils, characteristic of a diurnal hunter that relies heavily on vision and chemoreception to locate prey. The dorsal scales are smooth, without the raised keels found in many viper species, and they are arranged in 23 rows at mid-body. The scale count along the belly ranges from 211 to 250 ventral scales, with a single anal scale and divided subcaudal scales numbering between 55 and 70. But the most remarkable thing about the inland taipan's physical appearance is not its size or its shape. It is the fact that this snake changes color with the seasons, a phenomenon that is relatively uncommon among snakes and serves a direct thermoregulatory function. During the Australian winter, which runs from roughly June through August, the inland taipan's coloration darkens dramatically. The head and neck, in particular, can become a glossy, almost jet black, while the rest of the body deepens to a rich dark brown or near black tone. During the summer months, the same snake lightens considerably, shifting to a pale fawn, olive green, or straw color. The transition is not instantaneous. It occurs gradually over the course of several weeks as the seasons change. The purpose of this seasonal color change is straightforward. In winter, when temperatures in the outback can plunge to near freezing overnight, and the days are short and cool, the darker coloration allows the snake to absorb radiant solar energy more efficiently during its morning basking sessions. This is critical for a cold-blooded animal that depends entirely on external heat sources to power its metabolism, its digestion, its immune system, and its ability to move quickly enough to hunt and escape danger. In summer, when the ground surface temperature can become lethally hot, the lighter coloration helps the snake reflect more sunlight and avoid overheating. The head, which is consistently several shades darker than the body regardless of the season, plays a special role in this thermoregulatory strategy. The inland taipan can poke just the top of its dark head out of a burrow entrance or soil crack, exposing only a small portion of its body to the sun, while the rest remains sheltered underground. That dark head acts as a solar panel, absorbing heat and warming the blood flowing through the brain and the core of the body, allowing the snake to raise its temperature with minimal exposure to predators or the elements. It is a beautifully efficient adaptation to life in an environment where temperature management is a constant challenge. Beyond the seasonal color change, the inland taipan's appearance includes several other notable features. Many of the dorsal scales have a broad, blackish-brown anterior edge, and these dark-marked scales are arranged in diagonal rows that align to form broken chevron or herringbone patterns running down the length of the body. These markings are inclined backward and downward, creating an intricate geometric pattern that helps break up the snake's outline against the mottled clay and stone of its habitat. The ventral surface is pale, yellowish to cream, often with orange blotches that can extend onto the lowermost lateral scales, adding a flush of warm color to the underside. One detail that often goes unmentioned in casual descriptions is how small the scales are on the inland taipan's body relative to other large Australian elapids. The species name, Microlepidatus, literally means small-scaled in Greek. And this was the feature that first caught Frederick McCoy's attention when he described the species in 1879. These small, numerous scales give the snake's skin a fine-grained, almost polished texture that contributes to its ability to slide smoothly through tight spaces in the cracking clay and through the narrow passages of rodent burrows. The fangs of the inland taipan are relatively short compared to those of its cousin, the coastal taipan. Measurements of inland taipan fangs range from 3.5 to 6.2 millimeters in length, roughly a quarter of an inch. This may sound modest, but these fangs are hollow, highly efficient venom delivery needles that are more than adequate for penetrating the skin and muscle tissue of the small mammals that make up the snake's entire diet. And what those short fangs lack in length, they more than compensate for in the potency and volume of the venom they deliver. If the inland taipan's venom were a piece of music, it would be a symphony, not a single note. This is not a simple poison. It is a staggeringly complex biochemical cocktail, a mixture of dozens of individual toxins that work together synergistically to attack multiple organ systems simultaneously. While other venomous snakes may specialize in one type of toxin, delivering primarily neurotoxins or primarily hemotoxins, the inland taipan's venom does everything at once. It attacks the nervous system, it attacks the blood, it attacks the muscles, and it accelerates its own absorption into the body, so that all of these effects occur with terrifying speed. Let us start with the numbers that earned this snake its infamous title. The standard measurement for comparing venom toxicity is the LD50 test, which determines the dose of venom required to kill 50% of a test population of laboratory mice. The inland taipan's subcutaneous LD50, the most relevant measurement for actual bite scenarios, is 0.025 milligrams per kilogram of body weight when refined with bovine serum albumin, a substance that more closely mimics the conditions inside a living body. This number drops even further to 0.01 milligrams per kilogram. By any measure, this is the most toxic venom of any land snake ever tested. For comparison, consider these numbers. The coastal taipan, the inland taipan's larger and more aggressive relative, registers at 0.099 milligrams per kilogram, making the inland taipan roughly 4 times more potent. The Indian cobra, one of the big 4 snakes responsible for most snakebite deaths in South Asia, registers at 0.565 milligrams per kilogram, making the inland taipan more than 20 times more potent. And the North American eastern diamondback rattlesnake, perhaps the most iconic venomous snake in the Americas, registers at a comparatively mild 11.4 milligrams per kilogram, making the inland taipan roughly 450 times more potent on a drop-for-drop basis. But raw toxicity is only part of the story. The amount of venom delivered per bite matters enormously. And this is where the inland taipan's threat level comes into even sharper focus. The average venom yield per bite is 44 milligrams, and the maximum recorded dose from a single milking is 110 milligrams. This is less than the coastal taipan, which delivers larger quantities per bite, and far less than the eastern diamondback rattlesnake, which can inject over 400 milligrams. But because the inland taipan's venom is so extraordinarily concentrated, that relatively modest 44 milligrams of fluid carries vastly more killing power than the huge doses delivered by less toxic species. Researchers have calculated that a single average bite from an inland taipan contains enough venom to kill approximately 100 adult humans, or roughly 250,000 mice. Now, let us look at what is actually in this venom, because the composition is where the true biological sophistication reveals itself. The first major class of toxins in the inland taipan's venom is the neurotoxins, and these come in two varieties that attack the nervous system from different angles. The presynaptic neurotoxin, called paradoxin, is one of the most significant components, making up approximately 15% of the total venom by weight. Paradoxin is a phospholipase A2 complex, a large molecule composed of 3 subunits, and it works by infiltrating the nerve terminals at the neuromuscular junction, the point where nerve cells communicate with muscle fibers. Paradoxin disrupts the nerve terminal's ability to release acetylcholine, the neurotransmitter that triggers muscle contraction. Without acetylcholine release, the muscles stop responding to nerve signals, leading to progressive flaccid paralysis. The horrifying subtlety of paradoxin is that before it shuts down neurotransmitter release entirely, it causes a massive, uncontrolled burst of acetylcholine release, essentially firing every nerve signal at once before going permanently silent. This presynaptic damage is essentially irreversible in the short term. Even antivenom cannot undo it once it has occurred. The nerve terminals must physically regenerate, a process that can take days to weeks. The venom also contains postsynaptic neurotoxins, including a molecule called oxalipotoxin 1, which accounts for roughly 8% of the whole venom. Unlike paradoxin, which acts on the sending side of the nerve muscle junction, oxalipotoxin 1 acts on the receiving side, binding to the nicotinic acetylcholine receptors on the muscle cell surface and blocking them. This prevents any acetylcholine that does manage to be released from having its intended effect. The result is the same: paralysis. But the critical difference is that postsynaptic neurotoxin effects are potentially reversible. Antivenom can displace oxalipotoxin 1 from the receptors, and washing the toxin away from tissues in laboratory experiments has been shown to restore muscle function. This dual neurotoxic attack, one presynaptic and irreversible, one postsynaptic and reversible, creates a more comprehensive and faster-acting neuromuscular shutdown than either toxin could achieve alone. But the inland taipan's venom does not stop at the nervous system. It also contains a potent hemotoxic component, specifically a prothrombin activator that attacks the blood clotting system. This procoagulant triggers the conversion of prothrombin to thrombin at a massively accelerated rate, which in turn causes the rapid consumption of fibrinogen and other clotting factors in the blood. The result is a condition called disseminated intravascular coagulation, or more specifically, venom-induced consumption coagulopathy. What happens is counterintuitive. The venom first causes widespread microscopic clotting throughout the blood vessels, and then, because all the clotting factors have been used up, the blood becomes entirely unable to clot at all. the victim's blood becomes thin and watery, unable to form scabs or seal wounds. This puts the victim at severe risk of hemorrhage, both from the bite site and internally. The most dangerous possibility is hemorrhaging in the brain, which can be rapidly fatal. This coagulopathy can become established within 30 minutes of a bite and is one of the earliest clinical signs of envenomation. The venom also contains myotoxins, components that attack skeletal muscle fibers and cause a condition called rhabdomyolysis, the breakdown and death of muscle tissue. When muscle fibers disintegrate, they release their contents into the bloodstream, including a protein called myoglobin. The kidneys, which are responsible for filtering the blood, can become overwhelmed by the flood of myoglobin, leading to acute kidney injury or failure. Although no specific kidney toxins have been isolated from the Inland Taipan's venom, kidney damage is a recognized secondary consequence of severe envenomation, occurring as a downstream effect of the muscle destruction. And there is one more component that makes the Inland Taipan's venom particularly fast-acting. The venom contains a spreading factor, an enzyme called hyaluronidase that breaks down hyaluronic acid in the connective tissues surrounding the bite site. This effectively opens up the tissues and accelerates the rate at which the venom is absorbed into the lymphatic system and bloodstream. It is like a chemical door opener, clearing the path for the neurotoxins, hemotoxins, and myotoxins to spread through the body as rapidly as possible. The combined effect of all these components working together is a venom that can cause death in as little as 30 to 45 minutes if left untreated. The victim experiences a cascade of overlapping symptoms: headache, nausea, vomiting, abdominal pain, and dizziness in the early stages, progressing rapidly to coagulopathy, neuromuscular paralysis, muscle pain, difficulty speaking and swallowing, drooping eyelids, respiratory failure, and ultimately cardiovascular collapse. It is a multi-front biological assault that overwhelms the body's defenses from every direction simultaneously. And here is a detail that underscores just how thoroughly adapted this venom is to its purpose. Studies have shown that the venom of baby Inland Taipans is not significantly different in composition or toxicity from that of adults. From the moment they hatch, these snakes are armed with the full chemical arsenal. There is no juvenile version, no weaker training venom. Every Inland Taipan, from a hatchling barely longer than your forearm to a fully grown adult, carries the same devastating payload. The Inland Taipan is an obligate mammal specialist. In the wild, it feeds exclusively on mammals, primarily small to medium-sized rodents. This dietary exclusivity is shared with all members of the genus Oxyuranus and is unique among Australian elapid snakes. No other genus on the continent feeds solely on warm-blooded prey. And the Inland Taipan's entire lifestyle, from its venom chemistry to its hunting strategy to its reproductive output, is orchestrated around the population dynamics of a single species of rodent, the long-haired rat, Rattus vilicissimus. The long-haired rat, also known as the plague rat, is one of the most ecologically dramatic animals in Australia. Named for its distinctive coat of long, coarse-guard hairs over a softer underfur, this native rodent is found across the arid and semi-arid interior of the continent, inhabiting the same cracking black soil plains that the Inland Taipan calls home. In normal years, the long-haired rat is a rare and inconspicuous animal, restricted to small refuge populations near reliable water sources and good vegetation. But when conditions align, when heavy rains soak the outback and trigger a flush of new plant growth, the long-haired rat does something extraordinary. It breeds at an almost unbelievable rate, with females capable of producing litters of up to 12 young every 3 weeks. Within months, a small refugee population can explode into a full-blown plague, with rats numbering in the millions spreading across vast areas of the landscape, consuming everything edible, invading homesteads, filling every available burrow and crack in the earth. These plague events have been recorded across Australian history, documented in 1860, 1869, 1887, the 19-teens, the 1930s, the 1940s, the 1950s, the 1960s, the 1970s, and sporadically since then. They are a natural and recurring feature of the outback ecosystem, driven by the same unpredictable rainfall patterns that shape every aspect of life in the interior. For the Inland Taipan, these rat plagues are a bonanza. When long-haired rats are abundant, the snakes grow sleek and fat, their bodies swelling with stored energy. Their reproductive output increases, with females producing larger clutches of eggs, and sometimes even producing 2 clutches in a single breeding season. The snake population rises in tandem with the rats, a direct and visible response to food availability. But when the rains stop and the landscape dries out, the rats die off just as dramatically as they multiplied. The vegetation withers, the food supply collapses, and the rat population crashes, sometimes virtually disappearing from entire regions. And when the rats vanish, the Inland Taipans must adapt. They draw on their stored fat reserves, switch to alternative prey species like the plains rat, the house mouse, and small carnivorous marsupials called dasyurids, such as the coulter, and their own numbers decline. The snake population retreats, becoming scarcer and harder to find, until the next rain event triggers the next rat boom, and the cycle begins again. This boom and bust dynamic shapes every aspect of the Inland Taipan's hunting behavior. The snake is a diurnal hunter, most active in the early morning hours when temperatures are cool enough for sustained surface activity. It uses a combination of chemoreception, flicking its forked tongue to detect chemical trails left by rodents, and its Jacobson's organ, a specialized sensory structure in the roof of the mouth, to track prey through the landscape. When it locates a rodent, the snake typically follows it to its burrow or to a crack in the soil, cornering the animal in a confined space where escape is difficult. The strike itself is extraordinary. The Inland Taipan does not employ the classic bite and release strategy used by many venomous snakes, including its own relative, the coastal taipan. Instead, it uses a bite and hold technique, or more accurately, a rapid series of multiple bites delivered in quick succession while maintaining contact with the prey. The snake strikes with extreme speed and accuracy, envenomating with almost every bite, and often delivers 3, 4, or even more bites in a single attack that lasts only seconds. Because the venom acts so quickly, the prey is immobilized almost immediately, giving it no chance to fight back, flee, or inflict retaliatory wounds on the snake. This rapid multi-strike approach is thought to be an adaptation, specifically for hunting long-haired rats, which are formidable prey animals. Anyone who has handled a long-haired rat can attest to the power of their incisors and their willingness to bite. A snake that spent several minutes wrestling with a large rat, waiting for its venom to take effect, would risk serious injury from those powerful jaws. The Inland Taipan has solved this problem through speed, precision, and overwhelming chemical force. Despite its position as the apex predator of the cracking clay ecosystem, the Inland Taipan is not without enemies. The mulga snake, Pseudechis australis, is immune to most Australian snake venoms and is known to prey on young inland taipans. The parenti, Varanus giganteus, Australia's largest monitor lizard, shares the inland taipan's habitat and grows large enough to tackle even adult venomous snakes as prey. Large birds of prey also pose a threat, particularly to juveniles and smaller adults. For the Inland Taipan, the primary defense against these predators is not aggression. It is evasion. The snake's first response to any perceived threat is to retreat underground, sliding into a crack or burrow and disappearing from sight. The reproductive cycle of the Inland Taipan is tied to the seasons, and more importantly, to food availability. Mating typically occurs in late winter and into spring, coinciding with the period when the snakes are emerging from the cooler months and resuming more active surface behavior. Males engage in ritual combat during this period, a behavior that has been observed in the wild between large individuals. During these encounters, which can last approximately half an hour, two males intertwine their bodies, raise their heads and forebodies off the ground, and attempt to force the opponent's head down to the ground. They lash out at each other with closed mouths, not biting, but wrestling. The male that successfully pins the other's head to the ground wins the contest and earns the right to mate with nearby females. After mating, the female carries her developing eggs internally for a period before depositing them in a suitable nesting site. Females lay clutches of between 12 and 20 eggs, typically placing them deep in an abandoned animal burrow or a soil crevice where the temperature and humidity remain relatively stable. The eggs incubate for 9 to 11 weeks before hatching. Hatchlings emerge at approximately 47 centimeters in length, already fully equipped with venom glands and fangs, and their venom is every bit as potent as an adult's. There is no parental care. The mother abandons the nest soon after laying the eggs, and the hatchlings are entirely on their own from the moment they emerge. Sexual maturity comes relatively quickly. Males reach reproductive age at around 16 months, while females take longer, reaching maturity at approximately 28 months. In captivity, inland taipans can live for 10 to 15 years, with one individual at Australia Zoo recorded as living past 20 years. Lifespan in the wild is unknown, but is likely shorter, given the pressures of predation, food scarcity, and environmental extremes. The reproductive rate of the inland taipan is directly linked to food availability. In years when long-haired rats are abundant, females produce larger clutches and may even produce 2 clutches in a single breeding season. In lean years, when food is scarce, reproduction may be reduced or skipped entirely. This flexibility allows the population to track the boom and bust cycles of its primary prey, expanding rapidly when conditions are good and contracting when they are not. Now, about that name, the inland taipan is sometimes called the fierce snake, and this has led to decades of misunderstanding about the animal's temperament. The name fierce comes from William John Macleigh's 1882 description of the species, when he named it Diminia ferox. Ferox is Latin for fierce or wild, and Macleigh applied it to the snake based on its appearance, not any observed behavior. He had a single dead specimen to work with and no opportunity to observe the living animal. In the century and a half since, the name has stuck, and it has led countless people to imagine the inland taipan as an aggressive, attack-prone predator that will chase down and bite anything that moves. The reality is almost exactly the opposite. The inland taipan is, by virtually all accounts, a shy, reclusive, and remarkably placid snake. Many experienced reptile keepers who work with captive inland taipans describe it as one of the calmer, more handleable venomous snakes in their collections, though they are always quick to add that this does not mean it is safe. It is not. Even a placid snake carrying the world's most toxic venom demands absolute respect and caution. But in terms of temperament, the inland taipan is nothing like its more aggressive relative, the coastal taipan, which is notorious for its willingness to strike with little provocation, and which many herpetologists consider genuinely dangerous due to its behavior around humans. In the wild, the inland taipan's first response to any disturbance is to retreat. If it has access to a nearby crack, burrow, or other shelter, it will simply slide away and disappear. If retreat is not possible, it will adopt a defensive posture, raising its forebody off the ground in a tight, low S-shaped curve, with its head facing the perceived threat. This is a warning. It is the snake's way of saying, "I am aware of you, and I will bite if you do not leave." If the warning is ignored and the snake is further cornered or physically handled, it will strike. And when it does strike, it is devastatingly effective, fast, accurate, and delivers venom in almost every case, often with multiple bites. This defensive behavior pattern is important to understand because it explains why virtually all documented inland taipan bites on humans have occurred under very specific circumstances. Almost all bite victims have been herpetologists handling the snakes for study, venom milkers, extracting venom for antivenom production, or keepers maintaining captive specimens in wildlife parks. These are people who are deliberately putting their hands on or near the snake. In the wild, where the inland taipan lives in such remote and sparsely populated areas, the chances of an ordinary person encountering one are vanishingly small, and even if they did, the snake's instinct would be to flee, not to fight. When snake meets human, documented bites, antivenom, and survival, despite carrying the most toxic venom of any land snake on the planet, the inland taipan has, remarkably, never killed a single person as of the most recent reviews of the scientific literature. There have been approximately 12 formally documented cases of inland taipan envenomation, and every single victim survived. This extraordinary safety record is the result of three converging factors: the snake's extreme remoteness, its reclusive temperament, and the availability of effective antivenom. Before the development of taipan antivenom, the prognosis for anyone bitten by any species of taipan was grim. Prior to 1956, taipan bites were nearly always fatal. There are only 2 reported survivors of taipan bites in the years before antivenom became available. One of them was George Rosendale, a Gugu Yimithir man who was bitten at Hope Vale in 1949 and somehow survived without any antivenom treatment. His case was so severe that the nurses later showed him extracted samples of his own blood, which had turned completely black from the venom's effects on his blood clotting system. The story of how taipan antivenom was developed is itself a tale of heroism and tragedy. In the late 1940s and early 1950s, researchers at the Commonwealth Serum Laboratories in Melbourne desperately needed live taipans to milk for venom so they could produce an antivenom. But taipans were extraordinarily difficult to capture alive. In 1950, a 20-year-old man named Kevin Budden traveled to the Cairns area in far north Queensland to capture a coastal taipan for antivenom research. He succeeded in catching one, but was bitten in the process. Despite efforts to save him, Budden died the next day. His taipan, however, was delivered safely to the laboratory, and the venom milked from that snake and others that followed was used to develop the first taipan antivenom, which became available in 1955 and has saved countless lives since. The antivenom used to treat inland taipan bites is the same product developed against the coastal taipan's venom. It is manufactured by Seqirus, formerly BioCSL, and is made from horse immunoglobulin G, antibodies produced by horses that have been immunized with coastal taipan venom. Because the inland and coastal taipans are closely related and share many venom components, this antivenom cross-reacts effectively with inland taipan venom. Studies from the Australian Snakebite Project have confirmed that a single vial of taipan antivenom is sufficient to bind all measurable venom in the bloodstream following a taipan bite. Though multiple vials may be administered in severe cases or when treatment is delayed, the documented cases of inland taipan envenomation provide a window into what this venom does to the human body. One of the most thoroughly reported cases involved a 22-year-old male keeper at a public reptile exhibit in Florida, in the United States, who was bitten on the hand while cleaning the cage of a captive female inland taipan. Within 5 minutes of the bite, he experienced transient loss of consciousness, altered sensorium, nausea, headache, weakness, and severe pain at the bite site. Laboratory tests revealed profound coagulopathy, including an inability of his blood to clot, and he developed cranial nerve palsies affecting his eye movements. He was treated with 4 vials of Australian polyvalent antivenom and 1 vial of Taipan monovalent antivenom, all of which were expired products, with some having expired as long as 38 years prior. Despite the use of expired antivenom, the treatment was effective, and the patient recovered sufficiently for discharge within 48 hours. Another case, published in Toxin in 2017, involved a victim who was envenomated by a wild inland taipan while attempting to photograph one in an isolated area of South Australia. He reported drowsiness and blurred vision that progressed to ptosis, the drooping of the eyelids that is often the first visible sign of neuromuscular paralysis. He then developed difficulty swallowing and speaking. He was treated with polyvalent and Taipan monovalent antivenoms, was intubated for airway protection, and recovered after 3 days of intensive care, though he experienced a persistent one-sided eye paralysis that lasted about a week after the bite. The pattern across all documented cases is consistent. Inland Taipan envenomation produces a combination of coagulopathy, which can develop within 30 minutes, and neurotoxicity, which typically becomes clinically apparent within 2 to 4 hours. Some patients also develop muscle breakdown and kidney impairment as secondary effects. But with prompt administration of appropriate antivenom, full recovery is the expected outcome. Although the process can take days to weeks, especially for the presynaptic neurotoxic effects, which must regenerate naturally and cannot be reversed by antivenom alone. The key clinical takeaway from all reported cases is that early antivenom administration dramatically improves outcomes. Research from the Australian Snakebite Project has shown that patients who receive antivenom within 4 hours of a taipan bite have a median hospital stay of about 51 hours, compared to 175 hours for those who receive antivenom more than 4 hours after the bite. Early treatment is also associated with lower rates of neurotoxicity, kidney injury, muscle damage, and the need for mechanical ventilation. The International Union for Conservation of Nature currently classifies the inland taipan as a species of least concern. This means that, at a broad level, the species is not considered to be at immediate risk of extinction. Its population is believed to be stable, and its remote, sparsely populated habitat has provided a natural buffer against the kinds of direct human pressures, urban expansion, agricultural development, and deliberate persecution that threaten many other snake species around the world. But this classification should not inspire complacency. The inland taipan is a highly specialized animal, dependent on specific soil types, specific climatic conditions, and specific prey species. Any significant disruption to these ecological requirements could have serious consequences for the species. And there are several potential threats on the horizon. The first and most immediate is the impact of introduced predators, particularly feral cats and foxes. These invasive mammals have devastated native wildlife populations across Australia. And while their impact on the Inland Taipan specifically has not been well studied, they are known to prey on a variety of snake species and could pose a threat to juvenile inland taipans. Perhaps more significantly, feral cats and foxes also prey on the same rodent species that the inland taipan depends on for food, potentially reducing the availability of prey in areas where these introduced predators are abundant. Interestingly, one widespread ecological threat in Australia has had relatively little impact on the taipan genus. The cane toad, Rhinella marina, introduced to Australia in 1935 and responsible for massive declines in populations of many native predators that attempt to eat the toxic toads, has not significantly affected the taipans. The reason is simple. Taipans feed exclusively on mammals. They have no interest in toads, and therefore no exposure to the cane toad's deadly skin toxins. Some researchers have even suggested that the introduction of cane toads may have indirectly benefited taipans by reducing the populations of competing snake species that eat frogs and toads. Climate change represents a longer-term, but potentially more serious threat. The inland taipan's habitat is already one of the most climatically extreme environments on the planet, and models projecting future climate scenarios suggest that conditions in the Australian interior will become even hotter and drier over the coming decades. Intensified droughts, shifting rainfall patterns, and rising temperatures could destabilize the boom and bust prey cycles that the inland taipan depends on, alter the structure of its cracking clay habitat, and push the snake's thermal tolerance limits. Some assessments have classified the inland taipan as highly vulnerable to the impacts of future climate change on the Australian landscape. The cracking clay floodplains, with their deep fissures and complex microhabitats, may be particularly sensitive to changes in rainfall patterns that could alter soil moisture regimes and crack formation. The inland taipan has also vanished from parts of its historical range. The specimens collected from northwestern Victoria in 1879 and from near Burke in New South Wales in 1882 represent locations where the species has not been observed in well over a century. Whether this disappearance is due to habitat modification, changes in prey availability, or other unknown factors remains unclear. But it serves as a reminder that even seemingly secure species can lose ground without anyone noticing until it is too late. On a more hopeful front, the inland taipan's venom is increasingly recognized as a potential goldmine for medical research. The same molecules that make this venom so deadly to prey animals also have properties that could be harnessed for human medicine. The blood-clotting protein factor 10, identified in taipan venom by Queensland University of Technology researcher Liam St. Pierre, has shown potential as a rapid hemostatic agent for controlling excessive bleeding during vascular surgery and major trauma. While mammals, including humans, produce their own version of factor 10 in the liver, the snake-derived version is more stable and faster acting, capable of initiating clot formation within seconds. This could have life-saving applications in emergency medicine, surgical settings, and military combat situations, where uncontrolled hemorrhage is a leading cause of death. Beyond hemostasis, the broader field of venom-derived pharmaceuticals is flourishing. Venom components from various snake species have been studied for their potential applications in treating cardiovascular disease, chronic pain, blood disorders, and cancer. The neurotoxins in elapid venoms, which bind to specific receptor types with exquisite precision, have been invaluable research tools for neuroscientists studying the structure and function of acetylcholine receptors and other components of the neuromuscular junction. While specific Inland Taipan-derived drugs are not yet in clinical use, the ongoing study of this venom's extraordinarily complex biochemistry continues to reveal new molecules and new potential applications. Researcher Ronell Welton of James Cook University has noted that most of the contents in Inland Taipan venom have not yet been fully characterized, and that relatively little molecular research has been undertaken on taipan venom compared to better studied species like cobras and vipers. This means there are likely significant discoveries still waiting to be made in this venom, molecules whose properties we cannot yet predict and whose medical applications we have not yet imagined. The Inland Taipan, in addition to being the most toxic land snake on Earth, may turn out to be one of the most medically valuable. And perhaps that is the most fitting way to think about this animal as you drift off to sleep tonight. The Inland Taipan is a creature of paradoxes. It is the most venomous land snake in the world, yet it has never killed a person. It carries enough toxin in a single bite to end more than 100 lives, yet it is one of the shyest and most reclusive snakes on the planet. It bears the name fierce, yet it would rather disappear into a crack in the earth than confront anything larger than a rat. Its venom is a masterpiece of destructive biochemistry, yet that same biochemistry may one day save lives in hospitals and operating rooms around the world. Out there, right now, in the vast cracking clay plains of the Channel Country, where the Diamantina River braids across the landscape and the sun rises over a horizon that stretches forever, an Inland Taipan is coiled in the cool darkness of a soil crevice, waiting for morning. When the first light touches the red-brown earth, it will push its dark head into the sun, absorb that warmth, and begin another day of quiet survival in one of the harshest environments on the planet. It has been doing this for millions of years, long before people arrived on this continent, long before science gave it a name, long before anyone thought to measure the lethality of its venom. And if we leave it alone, if we protect its habitat and respect its space, it will continue doing exactly this for millions of years more. The most venomous snake ever measured, the gentlest killer you will never meet, the Inland Taipan. Sleep well.